And the subject of today's training session is time series analysis. So I hope you can see the screen well. If not, let me know. I will try to increase, but I'm using single monitor, so I think I did a good job of not having any small fonts. Okay, so the outline of the course is, so we will discuss what is time series and what is so special about it and why I decided to pull it into advanced training session. Some applications for time series analysis and what drives these applications. Time series models, how time series analysis is used, and primarily for anomaly detection and trend analysis and some other stuff. A few words about machine learning. I believe that you all heard about it. Please do not be scared. We will not go too deep into it, but I believe it's important to understand what it is. And we will also talk a little bit about signal processing techniques and how they're used in statistics and how actually statistics used in signal processing too. So disclaimer, yours truly is a signal processing engineer. So that is kind of my background. So first, major definitions. What is time series analysis? And I put this caricature with the bulk data because, I mean, people make typos and sometimes people are confused by same meanings of the different acronyms. And so time series analysis is acronymed as TSA. The only two things I would like to say, the statisticians were the first to use TSA as an acronym, and then came the government and make everyone confused. Also, statisticians used acronym PDF for probability density function, and it was done way before Adobe. Okay, so in time series, the data points are indexed or listed or graphed in order of time. And this is the biggest difference, and that creates a lot of interesting consequences. The time series data is considered in three ways. So first of all, it's a set of observations on values or value that variable takes in time. Second, it allows do cross-sectional data, look at different variables collected at the same point of time. So time give us that kind of reference. And you can do, of course, you can do a combination of the two. So let's go to the next slide. Just by the way, you hear me well and you see well the screen? Can anyone speak up? I do not see the...
Yes.
Yeah,
okay, thank you much.
Yeah.
Okay, so time is a fabric that plays things and records into natural order. So you've heard about space-time fabric that discovered by Einstein. So time is a part of that fabric. So time gives us distance between the records. So if you get in your records, for example, from kind of a machine source, like sensors, like something else, then this data is spaced by equal intervals. And this is very important. So basically, you can use mathematics to integrate or to differentiate anything you want. But if you do integration differentiation over time, it gives you kind of a physical meaning for what you're doing. So you integrate speed, you get distance. You differentiate speed, you get acceleration. And in nowadays, a lot of things on the internet can provide you data that can be integrated or differentiated. Also, the time reference, and we talked just in the previous slide about that, gives us the reference to fuse data. And if this data is coming from different sources, that fusion can substantially enrich your data. In my life, I have been working with acceleration sensors and compasses and gyroscopes, and using these three helps to correct the errors between them. So its time is Time is part of our life, right? So we can't avoid it, and we should know how to use it. Also, the timed records are in some natural order, and they are, if you use two records uh, timed together, then you can correlate them, and this opens very powerful ways to analyze the data. However, the consequence is you cannot throw away records without ruining the time fabric. If you have nulls, you have to fill them somehow. There are interpolations, there are various interpolation techniques. You have to fill these nulls. You can trim the data at the beginning or at the end, but you cannot throw the nulls or outliers. And I know the statisticians are kind of have that habit, so this is a warning. So let's look at what we are kind of very often interested in. So this is the prediction, and prediction may be two ways of, I mean, two types of predictions. So you predict what something will happen in the future, and that's a prediction of the future, and we know how it goes in most of the times. But also there is prediction for, let's say, known or called as in-sample prediction. So let's say on this slide I have a picture of our previous training. This is a murder versus illiteracy, and you collected this data in year 1, and then you collected this data in year 2, and your new illiteracy rate falls within that range from 0.5 to 3. So, but you do not have that, and you want to compare it, but you do not have that specific data for murder rate, right? So you can use your regression model to predict what would be murder rate for that illiteracy rate on a new data set. That would be in-sample prediction, and in fact, this is where the regression models work best. For out-of-sample prediction, so you got like illiteracy rate, let's say either very low, below 0.5, or very high, over 3, and then you go out of sample, and the predictions tend to be significantly less accurate. We're more interested maybe in this, but I mean, we need to know that they are way less accurate, especially, and I hope you remember that we talked about overfitted regression models. If your model is overfitted, I mean, you cannot imagine how it will go out of sample. It will go almost vertically up or down. So, so this was like a little bit kind of a look back into regression models and what they're better used for. And just I would like you to remember that best of all, use them for in-sample prediction. And if you have to predict out of sample, then I would give you some new techniques today, and we will look at that. So when you're dealing with time series, prediction is mostly understood as prediction of the future. So there are very many time series analysis applications. This is economic forecasting, stock analysis, budget, sales, whatever. I mean, census. A lot of things have been done in the past with the time series data. However, the reason why I decided to bring the time series analysis to the advanced training is that there are new drivers for time series, new drivers of timed data. This is again new thing called Internet of Things, and it may be coming this way, or it will just come is a smart building, smart car, other smart things. And in particular, I know that GSA is managing buildings, and you have sensors in these buildings. And these buildings, these sensors provide voluminous data on temperature, on electric power consumption. So those are sensors sitting in the buildings, sort of that's what makes it possible to call these buildings smart. And the data from these sensors is streaming in a very high volume. And there is like very much interest in kind of automatic, I mean, it is so much data that you have to use some automated methods to analyze it. Besides, I do not know how much it's applicable to GSA. So in industrial world, in manufacturing, all machines right now have various kind of sensors to detect or try to prevent failures. So those are vibration, my favorite acceleration sensors, temperature sensors. In the security applications, there are motion sensors. Motion sensors include image detection. So there is, and imagine you have we've all seen movies where detectives are looking at security videos, and in their case, they most know the time, and it may be like 2 hours or even 15 minutes of time to watch, and it's time tedious to watch from all possible cameras. But imagine you need to do a bigger interval of time, and here comes image detection and very sophisticated image recognition processes. So that's what drives time series analysis. So to summarize, the new trends of having sensors in pretty much everywhere creates voluminous data, and that drives statistical application, and it drives machine learning. And so that's why I have included introduction to machine learning into that training today. How are we so far? Not too fast, not too slow?
That's good.
Good, okay, thank you. So the other thing I would like to mention is that there is and there was and there is very fruitful cross-pollination between telecommunications and statistics. So statisticians are using some techniques that came from telecommunications. And of course, signal processing is using a lot of things from statistics. So we will be talking about filters, and mostly statisticians, okay, they use the word filter, they like it. So if you filter something by dimension of your data, that's not the filtering we will be talking today. It's not the filter that is applicable for time series data. So those are dimensional filters. So let's forget about that. We will be talking about frequency filters, filters that pass certain frequencies. So smoothing filter, for example, that everyone is familiar now, is a low pass filter. So it passes low frequencies and cuts off high frequencies. So if there is a low pass filter, there is a high pass filter. And then there is a bandwidth filter. And then there is a rejection filter. So filters have a very powerful technology, very well developed. I hope you do remember that I mentioned Mr. Chebyshev, the mathematician who made his contribution to statistics. He developed lots of filters, and we will be looking at two ways to smooth the data today. So both would be low pass filters, and you would see the slight difference, but it makes slight difference in implementation, but makes substantial difference in the results. The other thing that is came into statistics from telecommunications is Fourier analysis. And again, that is, how to say it, a heavy subject, a lot of math, good math. It is 18th century math. So Fourier lived in France. and Napoleon made him a governor of Egypt, I believe, at some point, because he was just a bright guy. And what he developed is a transformation that transforms time series into frequency domain. I think it's important to understand and to know what it is, because this is like a word that you will see. The good thing that in nowadays, many of the algorithms are already developed, and you can use some functions and get the results. So I will have some pictures to show that. The newer thing, so Fourier analysis developed in 18th century, has some limitations. So wavelets cover these limitations. We will use a wavelet in our practical session. We will develop wavelet ourselves, and we will use it. So what was also a kind of a good example of using statistics in telecommunications is correlation to detect signal in a noisy environment. So prime application and prime example would be like a radar is sending a pulse, and the pulse is being reflected by the airplane, and it comes back, and it is very, very weak. And it traveled lots of distance, and the reflection is not one-to-one, so it's very hard to detect it. But the good thing is you know what signal you've sent, so you know what to expect. So you put the received signal through the correlation analysis, and you detect the signal, and now you can measure time, the time that elapsed between you send the signal and you received it back. And then you can determine the distance to that airplane. So correlation is very well used in telecommunications. And so all these techniques cross-enhanced by both disciplines, and they're available to statisticians. So I do not want you to become experts in Fourier wavelet analysis. There are like 500 pages for each of them, but I would like you to remember that they exist, and we will talk a little bit more. So I think you should know that they exist, and you should know where you may find a good application for those, and when you will run into that application, then you would know where to look for answers. So how are we so far? Okay. Yes. Just enough for me to hear the noise that you're getting off mute, so I know that you're with me. Thank you. So what are the goals of time series analysis, and what kind of techniques are used? So the prime thing is trend analysis. So what is the major trend? What is going on? And for that, we use regression, which we already know how to create regression models, and we use smoothing. And we will talk more about that. The other thing is periodicity detection. So we have some kind of a time series data, and we would like to see if there are any kind of periodic tendencies in it. And for that, we may use spectral analysis, which is for the tools for spectral analysis would be Fourier and wavelets. That's why I mentioned those. Another thing is very, very interesting and very important is anomaly detection. And that comes especially when you have this voluminous data from sensors. So like, I would say, the acceleration sensors or gyroscope I worked with, so they can provide like 500 readings per second, 500 hertz. Your electric sensors may be giving you readings like 3, 4, 5 times a minute. But these frequencies are increasing. So the sensors are capable of giving more data, and you need to have some kind of a machine automated tools to do that. There are simple tools like thresholds, and there are more complex. Anomalies are very different, so we will be talking about anomalies more today. Another thing is when we forecast something, we would like to know what is the confidence, how accurate we think our forecast is. And for that, we use statistical descriptive statistics like variances. We analyze noises, we look at errors. So there are techniques. So that is also comes to us from statistics. And the last but not least, we detected something, and we would like to evaluate the significance of this anomaly or event. And for that, we use probabilities. So now we come into time series models. So we're talking about some of them. And this is like a caricature that I do not know if you can see it well, so let me increase. Okay. Oops. So this is a Turkish working in the data science department, and they have realized that the searches for gravy in Turkey and Turkish stuffing are going through the roof. And of course, they realize it as they're smart data scientists, they realize this is a potential threat. So this is how data science can kind of save your life, right? If you're a Turkey and no data science. So this is an example of kind of a cross analysis, right? You're looking at other variables, so two different variables, stuffing and gravy. So let's go back into models. So this is, okay, hold on a second. Let me, okay. So first way of creating a model for time series data is a simple moving average. It's essentially, it's like smoothing. It's essentially a low pass filter. It's very fast, very convenient, very efficient to review the trend. So on the graph over here, we have the stock market data with all these candlesticks, a lot of information packed into this data. But what we would like to know is just not to be distracted from everything happening. And I mean, there is colors showing whether it closed higher or lower. And I mean, I hope you remember. So those are like the candlesticks, but they kind of look like a box plot, only with some deviations. Like, so you would like to see the trend, and for that you do simple moving average, which is running average also, and you see the trend, and here it is. And the only problem with that is it is hard to turn it into a useful model because it's hard to parameterize it. I mean, turn it into equation that we can use for plugging in the parameters, the variables from the future regions, right? So if your process, the time, the data, yes, the time to data, the trend is linear, then it is sort of easy to parameterize it. We just compute the slope, we compute the intercept, and here it is, right? If it is like more complex than that, it's very, very hard to fit the term, the curve into it. Still, it is possible. So this is, but this is the simplest way to do time series analysis and to reveal the trend. So since I mentioned that we can use smoothing on something that has like linear model, right? It's like increasing only, right? There is something also very important to understand in a time series analysis, and this is called stationary, non-stationary processes. So, for example, the process on the top is called stationary, and there are the statistical means to, so first of all, you can see it can be approximated with a line. And by the way, this line will be horizontal, right? Which means that the mean does not change with time. So you can take the mean on this area, and you can take the mean this area and this area, and the mean will stay the same. And also what is makes the process stationary is that variance doesn't change much, right? If you take variance here and here, and it is not changing too much. So the process on the bottom, you definitely see it's going down. So the trend would be like sort of almost linear, but it's going down. So the process is not stationary, but anyway. So on stationary process, you can definitely use a model, create a model using simple average. On non-stationary, it would be a little bit more difficult, but if it is linear, you still can use it. Some statisticians are suckers for big words, so they call it statistical equilibrium. But I mean, the essence is that mean and average do not change. There is, I looked at various definitions, and some are kind of really confusing. I think I found like the simplest way to explain what stationary means. So once we can distinguish stationary and non-stationary processes, we can go to seasonal trend Loess decomposition. And so what this technique, modeling technique, allows us to do is decompose a non-stationary time series like this into trend. So we extract the trend. And by the way, it's also called sometimes as feature extraction. So trend is a feature. And we can extract, once we have the trend, we subtract the trend from this original signal. We get a seasonal periodic part of the signal of the series. And also we get the remainder, right? The remainder is the difference, right, between this and this and this. So now we have decomposed the signal that was kind of a sort of difficult for analyzing for modeling, and we have extracted the trend, and for that we can use the running average or moving average technique, and we got the periodic component of it, and we can analyze them separately. And that is actually, that's pretty complex analysis. I think all you should know is that it exists. So if you get something like that, you should probably ask for help. But I mean, you can extract the trend using run an average, then do subtraction, get this, and probably then successful. At least you can graph it, you can plot it, you can see the periodicity, you can check on your timeline how fast it goes. So that is kind of to some extent you can perform it yourselves. In some cases you would need to ask for help, but at least you would be able to formulate what kind of help you need. So another way to creating a model, to model an time series process, is autoregressive model. So autoregressive model is somewhat similar to moving average. And essentially, so it's in autoregressive model, the output depends on the previous values of the lagged values of the ones that happened before in time. So the forecast is being done based on several points from the past. And again, it is very, very similar to moving average. The difference is, so both are low pass filters. So moving average is what? You take, let's say 10 points before, you sum them up, you divide them by 10, and you get your average for that point, right? For that upcoming point. In outer regression model, you pretty much do the same, only when you sum up the previous points, you sum them up with the coefficients that are computed in a special way. So, and these coefficients, we will do this exercise next week. Nothing difficult. It gives better results for the out of sample predictions. So if you need to go out of sample, they give better results. So, but essentially, it's very much like filtering. Running average is very, very simple. Outer regressive model is a bit more complex, but not terribly complex. So I believe this would be the tool that you can use. So are we okay? I gave you just couple of very, very new things. Like, can somebody speak up? Sorry, have I lost the audience?
No, I'm good.
Okay, okay, thank you guys. Okay, so next is, again, I don't think it's something that you can use, but you should be aware of it. It's symbolic time series analysis model. So it is essentially, you digitizing your time series. You put some kind of a threshold, and whatever comes over it, you give it a symbol, right? You give it a symbol, and then you, again, the whole world of the information theory methods come up to your, become available to you, and you do that. It's very efficient on noisy signals. So I don't think you would be able to do it yourselves, but if you see like symbolic time series analysis methods, you should know where it is. And we said, okay, listen, just keep it away. When I'm not quite ready, it's like a very, very special thing, but it is mentioned in literature. So I think you should be aware of it. So now what I think you would be, the likelihood of for you would be doing quite a lot. So let's say this, whether it is a smart building with voluminous data, or you have any other time data, it is very often you would be looking for anomalies. You would like to find them, and you would like to detect them, and you would like to explain them and look for reasons, because those may be significant, right? We know they're statistically significant, but I mean, in some cases, it may be an outlier because it may be an error produced by a sensor, which happens, or maybe it's like something that would lead you to getting a Nobel Prize. Right. So that's where we kind of spend a little bit more time. So anomalies would be like four types. I think you can come up with different classification, but that's kind of, I think, covers most of the anomalies. So outliers. And outliers may be, again, it may be outliers to be thrown away. And we all know that you cannot just throw them away. You can replace them with some kind of interpolated value. Or it may be a cry system or a smart building is crying, your data is crying for something. But they're very easy to detect. So this exactly picture is showing you anomaly, like an outlier detected with a threshold. So the dotted line is a threshold, something goes up. So here is very, very simple way to detect an outlier. The anomaly can be contextual. So there are like constraints applied by other variables. So you look at in the context. So let's say you have a temperature reading, from your building that is like high for this season. So let's say it is summer, and all of a sudden your heater goes up. So for heater going up would be okay in winter, but not in summer. So this is contextual. So you put your data in a context. You use timelines to pull data from other sensors. Let's say outside temperature. So your outside temperature is like 65 or 70, and all of a sudden your heater went up. So that is an anomaly, right? Anomaly is saying something is wrong. Fix your equipment. Collective. Collective is accumulation of low probability events. So all of a sudden, so let's say you are used to deal with a process that gives you sort of random data. So let's say it may be data that comes in a normal distribution, right, pattern. And all of a sudden, instead of normal distribution, you see repeated numbers of some kind of a same value several times in a row. So it means collective, this accumulation. So this is an anomaly, and you have to detect it and treat it. So break of pattern. So you have some periodicity in your system, and all of a sudden it changed. And so the methods to detect it are correlation, wavelets, and machine learning. And that's why we will be talking about machine learning. So this is a link to an interesting site, an interesting company called Anomaly. So they have an article about how they detect anomalies in the weight of the, I believe, of the bag of rice or something else. And I use it because they have nice pictures to illustrate. So this is would be an outlier over here. Here would be an illustration of a collective anomaly. All of a sudden, so they measure in, like, let's say, number of bags over time, right? So they measure their bag weights, and the weights like this, and all of a sudden the weight went up, and so they probably say, listen, at this particular time, what happened in our manufacturing facility where we bag rice, right? And what happened here? Why all of a sudden it kind of get a little bit on the high end? Or let's say break of a pattern. Or so we have like a variance, high variance over here. And so pattern may not be necessarily time pattern or seasonality. It may be break of variance, right? So all of a sudden from high variance, we go to a low variance. And that's, again, that's an anomaly. So I like these illustrations. I mean, this is a bit techy. They talk about normal distribution. I think it's a good read. So lastly, the anomaly may be very, how to say it, hard to detect by simple means. And in these cases, we use machine learning. And the good thing is machine learning is now available to pretty much everyone. So actually, it's time for you to consider learning Python. I mean, if your purpose of attaining this training to be able to understand statistics better, then you don't have to learn Python. If you are working and you're kind of a data scientist and you see, and you see like the data from smart builders are coming to you, or you see some kind of patterns that hard to analyze, then I would highly encourage learning Python. Actually, there is like lots of this stuff in R, but Python is probably have a biggest community behind it. So just few words how machine learning works. So there are algorithms that are already packaged in these modules, and scikit is one of them. And so these algorithms can be trained. So you use data some data to train the algorithm to perform certain operations, and what algorithm returns you is a model. And that model may be looking for various things, especially if your data is multidimensional. So let's say you have data from temperature sensors, you have data from electricity consumption, some other things. You look at the doors being opened or closed. So you can correlate it together, plug it into algorithm, and algorithm will give you a model. So what's happened inside of the model is kind of pretty much brute force computations. So the algorithm inside of a model creates all possible permutations and pick up the ones that have produced smaller errors on this training data set or other criteria. So by the way, machine learning is not limited to time series analysis. And I already told you that I'm for Python. So below is a diagram. This is an example of kind of an anomaly happening. And you see you cannot detect it by a threshold because there are like variable values happening higher than that. There's just one spike. And yeah, you can do filters, you can do lots of things, but machine learning really works good on this stuff, especially if you need to put this data into a context. So few more words about machine learning. So there are two types of machine learning, supervised and unsupervised. And supervised means that you train your algorithm, and basically, I mean, you use your Python development environment, you import the this scikit, you pick up the model, you feed it with the data, and data has answers. And that you run algorithm through that, and algorithm creates an equation that, or set of equations that deals with that data and returns you a model, and you can use on another data. So this is being used for classification and regression both. And by the way, when we did regression analysis in Excel, that was machine learning. It was machine learning because we did not feed the equation ourselves. We just called the algorithm in Excel. We picked up the input range, which means that was our training set. And the algorithm returned us an equation. So, and we will be doing more of that next week in our training session. Classification is a little bit difficult. There are models for Excel too, but I don't think it's worth kind of going through those. And by the way, you cannot import them into JSA, onto JSA computers, and you're still on Excel 2010. So, so let's kind of remember that classification exists, but I would say for that, use Python, and Python is available at JSA library, so you can download it. Unsupervised learning is different. You do not have answers for your data, but you can give the algorithm some clues what to do. So, for example, clustering, how it works. You can plot your data, and then you can tell the algorithm to find if there is a center, is this data clustered over some kind of a center? And you may say, hey, listen, would you please use the brute force again and find, are there more than one centers? Are there three centers? And the machine is going and going and going, and since the computers are fast, it will find these clusters for the centers for you, and then it will cluster the values, your values around these centers, and you will get a picture. And if you, we're doing this in Python class, So maybe I will show you how it works, illustrated there. So just a few words about the classification. Again, something probably we will not be doing with Excel, but I think it's kind of easy to explain, and it kind of this explanation stays with you and helps you to understand other things. So we have a data set that is labeled. So we have a data set that's called squares, triangles, and hexagons. And we put it through the model training. So the algorithm analyzes the set, computes the error, right? So the way we do it, so we have all this, let's say how we classify them. We say that the number of vertices are so much, so 3, 4, 6, some other things, faces, whatever we, sorry, not faces, that lines. So the algorithm is being trained. Then we go take test data where the answers are hidden, and we see how well it works, and then we use it on a new data, and here are our predictions. So this is called supervised machine learning, and you already know a little bit of it, not in terms of data classification, but regression analysis. So you already very much, I mean, don't be scared by machine learning, you already know it, a little bit of it. But since machine learning is such a kind of a buzzword nowadays, I would like just to show you what it can be used for. So we talked about regression, right? And the regression is talk about forecasting. And forecasting means that you go outside of your data set. Sorry, outside of the range of the variable that you're predicting on. Predictions means, I think, when you go inside, so this is in sample predictions. Forecasting is probably outside, out of sample predictions. You can use it for optimization. So regressions, we know that, and even Excel can do that. Classification, so we cannot do it in Excel, but I will just explain you that. So clustering, we talked about that. This is unsupervised learning. A dimensionality reduction is, I mean, do we need to keep looking at all dimensions of our data, or something can be thrown out? And reinforced learning is something very interesting. You reward your algorithm for good decision, and this is actually the connection. So algorithms are just brute force, right? But on top of the machine learning, you can put artificial intelligence, which is some reasoning agent, and a reasoning agent can use some, I mean, like we know with humans, right? So we can teach ourselves by rewarding ourselves with good things and kind of punishing the bad things. So here it is, reinforced learning. So I think I gave you kind of an overview of the machine learning. And the only other thing I would like to talk about, so before leaving it alone, is just give you the big picture. So machine learning belongs to artificial intelligence, and it is somewhere in the middle. But the foundation for the machine learning, this is supervised learning, unsupervised learning, and reinforced learning that we just kind of looked at. They are also called statistical learning. So this is where statistics is used heavily. Heavily used these things that we learned. The central tendencies are used here, and the variance analysis is used, all descriptive statistics, and a little bit more like all these things are used inside of the algorithms that are doing this fancy error minimization work. Any questions about machine learning? Okay, are you with me? Okay.
Yeah.
Yeah, thank you. Okay, so we just looked that there are many ways of creating the model for your time series. So how would you pick the best one? And model parsimony, Occam raised the principle, or colloquially known as keep it simple principle. So you pick up the one that has smallest number of parameters, simplest relationship among the parameters, and you make fewer assumptions. And this means the less of the parameter, the less of the constraints you apply to your model, the more generalized it is. And generalization is good because you are going to apply to not the data, to other set of data than the data you trained on. However, in our world, so especially if you go in and using the machine learning, you have no idea what it and how it analyzed and what it did internally. So in some cases you do. And so, for example, if you build and using a neural network, you decide how many internal layers you can use, and then it gives you kind of some understanding of what complexity is. If you're doing the regression analysis, also you can see is it linear regression? Okay, we got multilinear regression. Okay, sort of okay. Polynomial, okay. Order 2, okay. Order 3, 4, 5, 6, no, don't go there. Logarithmic or exponential, again, gives you smooth curve, should be okay. Anything curly, no, don't go there. So this is how to choose the model. Okay, so now we come into signal processing. And how signal processing is can simplify the life of a statistician, and how engineers are using statistics. So the picture on the right is an illustration of the Fourier analysis. So Fourier analysis allows us to do a transformation which replaces the timeline on the horizontal axis, on the x-axis, with frequency line. So what is frequency? Let's go back to this slide. So when we doing this smoothing filter or moving average filter or running average filter, so what essentially we're doing, I called it low pass filter. So what it does, it cuts this kind of fast fluctuation. So if you would say over a period of time from here to, let's say, here, the trend was pretty smooth. However, the initial time series, the original time series, made so many, you see, they even condensed it into this candlesticks, right? Because there is so many fluctuations. So fluctuation means more changing in time. More changing in time means more frequent. So that's where frequency comes in. So frequency and time are in reverse relationship. So what Fourier has discovered, again, this fascinates me. He did it in 18th century. So he discovered this formula that converts, and this is actually this kind of simplified version of it, converts the time into frequency. And it gives us very, very powerful, very interesting tool for analysis, especially when it comes to periodicity detection. So here is I have created a, and we will do it in class too together. So this is a transmitted signal, which is a simple sine wave, and this would be an interference signal, and that's another sine wave with a different frequency. And then we can take noise. And noise has all frequencies. In this case, it is called white noise, and white noise is a Gaussian noise, and that means it is normal distribution. So so here it is. I mean, don't look for the Gauss curve here, because this curve is in time. Gauss curve is built around averages, right? Sorry, around the values. So it is Gaussian noise. If you would like plot it like a scatter plot for the values, you would have some kind of a average over here, and then you would have pure Gaussian curve. So it is like uniform in time. That's Gaussian noise, and this is the sum of the three. So that's how it looks like. That's how it looks like. So what we can do in terms of analysis, so we can apply just smoothing filter, very simple, low pass filter, and low pass filter retrieves the signal which is pretty much close, very close to the original form. Very simple technique, cut it off the interference and noise together and retrieve the signal. Here is something I would like to point you to. So the filter, to do its work, and all filters need to collect the previous data, and that causes filters latency. So the better your filter is filtering, usually the high is the latency. And there are many ways how to build filter mostly efficient, and there's a huge science, thick books, but just so what latency means, that the result is becoming available to you only after some time, till the filter will fills its buffer, and it probably will continue a little bit longer. So the signal is maybe already over, but your filter is still producing result, and since the buffers are not filled, so it's kind of a distorted result. So when you're applying filters, you need to understand that you're probably it becoming accurate only after some time, and not till the end of your signal, right? So okay, so this is a simple way to detect a signal, and we've been so lucky because the interference was of a higher frequency, so more periods, more fluctuations, more changes in time, and so is noise, right? So there's more higher frequency, and we've been able to deal with this with the low pass filter, and actually this is why this running average, moving average, outer regression, all kind of low pass filters are so popular around statisticians, because in most of the cases the not interference, but the noise is usually coming at a high frequency. Everything, this random component of that kind of a accidental causes, they come in at a high frequency, and they can be dealt with the smoothing filters of different kind, and that's why engineers are kind of making fun of statisticians, because they pretty much know only low pass filters. But what if the situation is reversed. And here comes Fourier analysis. And so with the Fourier transform, you transform the signal from a time domain into frequency domain. So this is on horizontal axis, you now have frequency. And what is very interesting is that this sine wave in time, it looks like that. After you apply Fourier transform, it looks like this. And if it is a pure sine wave, it is just rods sticking out, just one line. And the cleaner is your signal, the cleaner is your sine wave, the narrower is that line. If it is like some impurities, it would be broader, it will have some kind of a shape. But again, it will be mostly confined to some kind of a area of frequencies. So is, in my example, the interference was, again, I choose intentionally the sine wave over different frequencies. So here we got another very, very clean picture. So if it would be reversed, we would have a rejection filter. If this would be an interference and this would be a useful signal, then we will put rejection filter over here and we would solve the problem. Noise is kind of a more difficult because noise, especially if this is a white noise, it covers all of the spectrum. And you cannot deal efficiently with noise. You have to use other techniques. And that's where correlation comes in play. So if you know what kind of signal you're looking for, like an example I gave you with a radar, so your signal is very, very weak. It's actually maybe weaker than noise, but you know the shape of the signal, you know the shape of the signal that you sent, so you can use correlation technique. And actually what's more interesting is, so you are sending this, the radar is sending its signal, it's sending pings time after time after time. So what you can do on the receiving end, you can detect it once, detect it twice, detect it 10 times, 100 times, and you can sum them up. And in this case, you sum up the signal, correlated, you pass it through the correlation filter, and when you sum it up, the signal is summed up arithmetically, and the noise is summed up geometrically, which means the noise disappears and the signal is increasing. And finally, you have a very, very clear picture. So on a repeating periodic signal. So to my big surprise, I managed to go through all of that stuff pretty fast. I mean, are you okay? Have you been able to follow it?
Yes.
Okay, thank you. So now let's talk a little bit about what we will be doing in class. So one of our own, one of my Python students provided very interesting time series data. This is data, electric consumptions at buildings. And so you may see this is like 1, 2, 3, 4, 5 spikes, I would say, in data. And so this can be interpreted, or actually is interpreted, as 5 days a week. And then there is a long weekend. And the beauty of the time series is that this distance between the spikes in the data can be measured, and we can see, hey, listen, this is the distance was like equal. So this is day 1, this is day 2. So this looks like 2 days, and this looks like more days, 3 days. So so we can do some analysis on that. So, and we will be doing it. We will detect long weekends. And the beauty of that example is that we will be able to do it in Excel. So we will be also practicing auto-regression, moving average a little bit more. Is there anything you would like to kind of, that since this is our last training session, anything you would like me to address during that last session upcoming? Any questions? Yeah. So, any questions over today's material? Okay, then I guess we fulfilled the training. Let me check if I captured everyone. So I have 18 people. Yes, please do not leave meeting. I'm just trying to make sure that I have everyone recorded. Sorry, just a second. I've seen there is a question. Gail, would you please be more specific? And actually, you have my email. Please tell me what exactly you're looking for. I have a lot of resources. I will send you something that you would. I mean, just please be more specific with what are you looking at. Just send me an email. Okay. Then I would say thank you very much, and I will see you next time. I'm stopping the recording now.